Hey everybody. Alright, this is the asynchronous component of the lecture series for this week. Continuing where we left off. We're talking about ibuprofen and I think oxalinic acid and a couple other compounds. One thing I got slightly wrong that I'm going to correct real quick. We talked about ibuprofen and the synthesis of it, and there's a reduction of an alcohol that I kind of forgot about, and then I think I gave the wrong reagent. It would work, but I'm just going to mention the more common reagent that's used in the commercial synthesis, one of the many commercial syntheses of this drug. So let's just get to that point. So they start with isobutylbenzene, and then they attach the stuff, the alcohol and the carboxylic acid. So remember that what they did was they kind of attached, first they attached an acetyl group with the Friedel-Crafts reaction, 2 carbons. Then they attached a nitrile, and then they hydrolyzed the nitrile to the carboxylic acid. Okay, so then the question was, how did they remove the alcohol? And I mentioned using acid and like a hydride source, H-. So essentially, acid like HCl would protonate it, make it water, right? Turn it into a water type thing, and then it would fall off, and you'd have a carbocation, a plus charge, and then you'd attach it with the H-. And that is one way to do that, but that's not the actual commercial method. What they use commercially is only slightly different. Let's actually redraw it. That makes the carboxylic acid, yeah. They use HI, red phosphorus. Red phosphorus is a super strong reducing agent. It's also called P4, phosphorus 4. So it's an electron donor, and it reduces stuff, right? So in a nutshell, yeah, this kicks off iodide, make water, and water falls off. So water falls off, and then you get isobutyl with a carbocation, and essentially red phosphorus will give this 2 electrons, and it becomes a negative charge, and then it grabs a proton from water or something. So this gets reduced. H means reduction, so red phosphorus acts as a reducing agent. Okay. Other thing I wanted to mention, just while we're talking about NSAID drugs and something like ibuprofen, is that Naproxen, which is called Aleve, is actually made the almost identical manner. I'm not going to draw that out. I'm just going to show the structures. So if you take for Naproxen, which is a naphthalene. What's a naphthalene? Well, this is naphthalene. Naphthalene, which is also naphthalene's mothballs, so it kills moths. It's a fused aromatic system. So you have a benzene and another benzene. That's called naphthalene. You have methoxynaphthalene. They do essentially the same exact thing to get to the final drug, naproxen. Benzene, and I won't show it. But anyway, now you know how ibuprofen's made, and also the related drug Naproxen, which is another NSAID drug. Okay, cool. And real quickly though, both ibuprofen and Naproxen are in this category of non-selective cyclooxygenase inhibitors. COX-1 and COX-2. Compared to those kind of fancier, like selective COX-2 inhibitors that have sometimes like cardiovascular problems. Okay, and you can kind of see, you know, the similarity of the molecules that you'd think they might actually bind to maybe the same enzymes, and that seems to be the case with these. And they both have the carboxylic acid, which I think is important for binding. Okay. One more thing before we continue from where the synchronous lecture left off. I just realized I forgot one compound. It's a pretty simple one, but it goes along with this theme of aromatic chemistry. I just want to sneak it in here real quick. It's B. It's 5B. That's why earlier, you know, we jumped from 5A to 5C, and that's because I forgot one. Okay, so this molecule is called Trifluperidol. A lot of these peridol substances are antipsychotic drugs, and this is also an antipsychotic drug. But what we like about it is it has really cool, simple organic 1, organic 2 style chemistry, and it's kind of aromatic chemistry also. So that's why we're gonna mention it real quick. Alright, so, and a lot of the antipsychotic drugs are dopamine receptor antagonists. I think it's a specific subtype of dopamine receptors. D2, I think, is one of the types of dopamine receptors. And it's a common target for antipsychotic drugs. It's just a simple small molecule scaffold. So how do they make this stuff? Using their simple chemistry. Well, it's pretty easy. Here's the molecule. It's fluorobenzene, ketone, carbon, 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 nitrogen, alcohol, CF3, and so they kind of they build this molecule really easily from that bond. They can make that bond really easily, and they can also make this bond. So they basically start with fluorobenzene, and then they just kind of attach the middle piece and they attach the right piece, essentially. So that's pretty cool. So how do they do it? Start with fluorobenzene, and using our Chapter 15, Chapter 16 chemistry. First question is is fluorine a orthopara director or a meta director? Do you remember? We talked about how alkyl, like isobutyl, like, you know, with the ibuprofen, alkyl things like some kind of carbon chain, those are orthopara directors, and they're slight activators. We also talked about how oxygen is also an orthopara director, right? Oxygen. And the lone pair on oxygen is an orthopara director. Okay, this is also an orthopara director, and the reason is the lone pairs. The lone pairs on fluorine kind of help, you know, they kick in onto the benzene, and it essentially activates the para position here. But there's also, it's weird because this is not an orthopara activator. Activator is like a fast, you know, speeds up the reaction, which is what the others were. The alkyl one and the oxygen one were orthopara activators. This is called Orthopara Deactivator. That's another organic too thing of like it's deactivating because, and it slow, you know, it slows the rate of the reaction, and that's because the benzene is sucking electron density onto the fluorine. It's pulling its electron negative, right? So we have the little cross thing with the arrow, and that suggests the fluorine is sucking electrons from the benzene, and that's a deactivating effect. Okay, so anyway, fluorine and the other halogens are all orthopara deactivators. Okay, so anyway, what do we got to do? We got to just kind of attach the middle piece and then attach the right piece. So this is very easy stuff. This is another simpler EAS reaction, or it's kind of like that. Well, EAS, that's one thing it is. Electrophilic aromatic substitution. You also need some aluminum trichloride in there. It's an EAS reaction, like all the aromatic reactions we've seen. But we also added the other name, which is Friedel-Crafts Isolation. It's the name of this reaction. And this is what we did, the same thing with ibuprofen synthesis. So these two things kind of talk to each other, and then the chlorine falls off, and then the benzene attacks the carbon. Yeah, that's what the Friedel-Crafts isolation is. Okay, so anyway, that just attaches the fluorobenzene into that piece. Then you got a ketone, carbon, 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 chlorine. And now they basically just attach that other piece and kick off the chlorine. So this is a super easy synthesis. HN, 6-member ring, alcohol, trifluoromethylbenzene, CF3 down there. CF3, okay? CF3, just like there. And what's the mechanism of this step? SN2 kicks off, and we're done, and we have the final product. Okay, cool. So that's what 5B was that I forgot in my other lecture. And C was oxalic acid. That was that DNA gyrase inhibitor antibiotic drug. So that's where we did that one last time. So I'm not going to do it again. Alright, 5B, 5C. Okay, so we're back on track. Sorry about the little detour. Now we're back on number 6, which it was dealing with kind of like carbonyl reactions, you know, ketones and aldehydes, enols, enol, which is was it enol again? It's like that. Those things are nucleophiles. They'll go attack things. Aldol reaction, etc. All right, so we just finished ketonazole. That was that kind of cool antifungal drug with the weird acetal and the linkage off the acetal. Now we're on to B, which is a very popular drug that can be made very simply using this enol chemistry and actually kind of like an aldol reaction. It's called Warfarin. Warfarin, you may have heard of that. It's a very popular anti-blood clot drug. Or you could say it's a blood thinner. And there's a lot of conditions that are treated with a molecule like warfarin. Things like heart disease, stroke, embolisms, and disease that is related to clotting. But blood thinners are a very, very common drug for a lot of diseases, and we'll talk about the biochemistry of it a little bit also. They're also called another name for this kind of molecule is called an anticoagulant. Coagulant it would be, well, an anti-clotting drug. Okay. Warfarin also has a couple other names. I think the most common commercial name is Coumadin. Okay, Coumadin. All right. I think, yeah, it's a pretty popular prescribed drug. I think there's like probably like 14 or 20 million prescriptions every year for it. Let's talk about the chemistry of it. It's really simple to make this, and it uses our themed reactions here related to carbonyls, enols, and aldols. It's a single-step synthesis, which is kind of cool. So how does it work? What is the molecule? And then we'll talk about the biochemistry of it a little bit. All right. So warfarin, I'm going to just draw it down here on the right. Is benzene and oxygen, OH, and then another little benzene over here, and a ketone. Okay, so they can make it in a single step by disconnecting right there. So they kind of take the left piece and react it with the right piece, and it just makes the product. Alright, so let's just go back then to the starting material. It's just this benzene. Okay, like that. And oh yeah, what do we call a cyclic ester? A cyclic ester. We've heard the word for cyclic ester because it's an ester that's cyclic. It's a lactone. Okay, so they have this lactone thing here, and it becomes the lactone thing over there. And then all they do to do the reaction is a Michael reaction, which I'll draw. I'll review the mechanism. It's a really easy mechanism. Okay, so essentially this thing is going to attack this thing. How does it do that? And why does it do that? Well, what's this thing called? This little unit here, OH in the alkene, we call it a enol, right? Do you remember anything special about an enol? It looks like an alkene and an alcohol, right? Enol, yeah. Any reactivity that you might remember of an enol, of this little enol thing? Well, enol is nucleophilic, meaning it likes to attack stuff. And it can be a nucleophile. This thing can be an electrophile. It can this can just attack this. And when you have the alkene next to a ketone, this will actually attack at the alkene position and then push the electrons towards the ketone. And that had a name also. Do you remember what the name is? When a nucleophile, enol or enolate nucleophile attacks an alkene next to a ketone. It's a human male name. It's a Michael reaction. Michael reaction. Okay, and so what actually happens then is I'll just sneak in there and erase a little bit. Okay. Lone pair swings down to make a double bond, and then this double bond attacks this double bond, and that's what the Michael reaction is. Then what happens? Anything else? Is that it? Nope, it keeps going all the way to the ketone. So it attacks there, this double bond goes there to make a new double bond, this double bond breaks and pushes electrons onto the oxygen. And that just snaps those two things together. It's a pretty simple reaction, and it gets us basically here, but there's an extra step, and I'm just going to draw what we get before we finish it off. Alright, so after all of this happens, we have our benzene. We got our 6-member ring, the oxygen at the bottom, ketone, ester, yeah. Ketone with a proton on it, and a charge. Long bond there, phenyl. And a negative charge up top. Oops, sorry. Okay, can you see it? Alright, good. Okay, so just to finish this, this is just really not even a reaction, it's just a little mechanistic step to convert this intermediate to this product. So all that happens is two things. One thing is that a base takes this proton, base takes that proton and pushes the electrons back onto oxygen. That's easy. See that? Base takes proton, reform a double bond, and push electrons up onto oxygen. And that gives us the, we get our enol back. So we start with the enol, attack, we get a ketone, and then we regenerate the enol. And that the reason it does that is because this double bond and this double bond are happy when they're in conjugation. They're like next door like that. And then the other thing that happens is really easy. This oxygen swings down, and then this just grabs a proton from solution, water, something. So that reforms the ketone right there. Okay? So those are just kind of little extra things that happen from this intermediate, and sometimes they put brackets around the intermediate too. Okay, a little bracket. Okay, all right. So now we have warfarin, and what does it do, kind of biochemically, to cause anti-blood clot behavior, and as a pharmaceutical? How does it do that? Okay, so let's draw the kind of like what this inhibits and how does it do that. Alright, so this inhibits an enzyme called vitamin K epoxide reductase. Vitamin K epoxide. We remember what an epoxide is? Epoxide. Epoxides are those little 3-member ring with the oxygen. Vitamin K epoxide reductase. What does a reductase do? It reduces things. So basically what this does is it's going to reduce an epoxide. Okay. This enzyme is called VCOR. Not exactly sure. Vitamin K, I don't know what the O stands for. But anyway, that's okay. So what does it do? What does the enzyme do? So it's going to take essentially a molecule called vitamin K epoxide. Let's draw that out. And then it's going to reduce it. And that's going to ultimately lead to blood clotting, like a reduction in blood clotting factors. Okay. So vitamin K epoxide, I'm going to draw that first, is this molecule. Benzene, carbonyl, carbonyl. Epoxide. There's the epoxide. And then just a bunch of stuff. So we got a CH2, alkene, carbon, 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 carbon. Okay, so, and what this enzyme does is it selectively reduces the epoxide. So that's what the enzyme does, and we're going to inhibit the enzyme. And this stuff's called vitamin K epoxide. Sometimes people kind of assume the word vitamin would suggest amine, because like amine, but this is a molecule with no amine in it. So, but anyway, vitamins are kind of often like kind of essential nutrients, right? And they all have kind of different interesting structures. Okay, this little unit in the molecule, if this had a name, does anybody know what that's called? Actually, just like that. Yeah, this is something you may have heard about in biochemistry or something. It's called a paraquinone. Let's draw that. Paraquinone. Okay. And anyway, so when this gets reduced, what does the structure look like? Then we'll talk about where vitamin K comes from. So the big thing is that epoxide's going to be gone. So let's draw that. Okay, we got our benzene, and then we have hydroxy. Alright, and then we have carbon-carbon, double bond, blah 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 blah, methyl. Let's draw that nicely. Methyl. Blah 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 blah, methyl. Blah 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 blah, methyl, methyl. Okay. So the big thing is the epoxide goes away, and now we have this thing, and this is not this is a paraquinone. This is not a paraquinone anymore. Anybody know what that is called? And assuming we have a double bond there, which we do because we're the benzene. So if we have that, that's not a paraquinone. It's called a parahydroquinone. Parahydroquinone. Okay. Para because it's opposite sides. Hydroquinone, and so hydroquinones are these quinones, Q-U-I-N-O-N-E, that have hydroxy groups on them. That's what a parahydroquinone is, and that's just called a paraquinone. All right, so we got that. So how does that relate to blood clotting? Well, this molecule is used in the generation of blood clotting factors. Blood clotting factors, and there's a couple of them. 2, 7, 9, oops, XI, and 10, factor 10, which is a big one. And these are basically involved in the process of blood clotting. Okay, so essentially by inhibiting this enzyme, we essentially shut down blood clotting through this process. Where does vitamin K come from? Like a lot of vitamins, we get it from diet. So dietary vitamin K. That comes from certain foods like green leafy vegetables. Brussels sprouts. Broccoli, things like that. Okay, and so people that are on blood thinners, in addition to taking a drug like Warfarin, they often have dietary restrictions of like not getting some of these vegetables, which sadly are actually healthy in other regards, but and everything's taken in moderation or whatever. But somebody should probably avoid lots of food with vitamin K in it to also sort of prevent the blood clotting from occurring, so their blood stays thin. Okay. Any guesses on what the structure of vitamin K is? If this is vitamin K epoxide, and knowing an epoxide is kind of a reactive functional group, do you think that vitamin K is consumed dietarily has the reactive functional group? Probably not. So yeah, anyway, so vitamin K, the molecule vitamin K, is the same molecule minus the epoxide. I think there's just a double bond there. So it is also a paraquinone, and then the net reaction converts to the parahydroquinone. Okay, all right, so we're cool with that. And all right, what else do we want to talk about here? Let's see. Okay, one more thing I kind of want to talk about. I just realized I spelled broccoli wrong, so let's fix that. I think it's 2 C's. Broccoli. Okay, one of the things I want to kind of mention as we're going to slowly start wrapping up this chemistry discussion and moving on to pharmacology and a little bit of toxicology and things like that, is the idea of potency, right? And a molecule like Warfarin, how do we measure potency? And potentially toxicity, right? For it to be a good commercial drug, which it is, it should be potent and efficacious, but not toxic at the concentrations that we use it as a drug, right? Okay, so just as a brief introduction, and we'll go more in depth later, let's just mention a couple of the parameters that we might consider. One of the parameters is IC50. I'm gonna briefly introduce it now, and then we'll talk about it a little bit more later. IC50 is the inhibitory concentration that gives 50% decrease in a function of like a protein or enzyme. Sometimes it's measured in a cell, sometimes it's just measured on the isolated enzyme. So we're not going to get into that detail here. I think this is the isolated enzyme. VCOR. So as a measure of potency, IC50 of Warfarin, the drug, on human VCOR, which is the vitamin K epoxide reductase, is about, we'll say 1 to 4 micromolar. So it varies a little bit based on measurement, but roughly 1 to 4. So, I mean, the meaning of that, of course, is that if we can sustain a concentration of around 1 to 4, so maybe 2 micromolar, like in a human, so within their blood and the volume the volume of blood in the human, if we can measure, if we can maintain that concentration, then we get this blood thinning activity. Okay. All right. So that's, and again, I'll explain IC50 a little bit later, and I'll draw little graphs that show the real meaning of that. But for now, just consider that as a measure of potency. So what is the what could we compare that to in terms of toxicity? I mean, a toxic concentration in a human is you can measure that, but a pretty easy way to measure this is almost like a toxic concentration, like in a rodent, which rodents have a lot of the same biochemical pathways as a human. That is basically the way we do this in pharmacology. So let's just look at the analogous numbers, toxic or lethal concentrations in a rodent. And an example that we frequently use is the concept of LD50. So LD50 is the lethal dose that would basically kill a half of a population of a rat or a mouse or something like that. And that's pretty much still the way that we do this in pharmacology. And it's not a concentration, it's a dose. So how do we measure dose? Okay, so the IC50s in micromolar. The lethal dose of warfarin in a rat is 186 milligrams per kilogram. So that means 186 milligrams per kilogram of a rat body weight, and of course a rat doesn't weigh a kilogram, so we have to kind of normalize this to figure out ultimately the concentration. I'm going to give the concentration in a second, and we'll do the calculation, I think, in the next lecture. But anyway, that's the lethal dose that would kill the half of a population of rat. For a mouse, it's actually a larger number, so we'd say it's less toxic even for a mouse. So for a mouse, it's 374 mg per kg. Okay, and so there's actually we require more of a dose, and you could basically say, well, I mean, these doses are pretty high even for a kilogram. And that would suggest that it's actually a fairly non-toxic drug, and that is the case. Okay, so what I'm going to do is I'm going to just leave a couple steps out, because we're going to do the calculation next time, and I'm just going to jump to we're going to basically convert these to micromolar for a rat and a mouse, and that is there's a couple of steps of the calculation which we'll just do in the next lecture. But I'm just going to give you the numbers right now, and that'll just confirm that this is really not a very toxic substance. LC50 is lethal concentration, and that it turns out to be about 9,400 micromolar for a rat, and 15,200 micromolar for a mouse. And so, ignoring the differences between a human and a rat and mouse, and there are definitely a lot of differences, but we're, I mean, both mammals, and there are a lot of similarities as well. You could say, well, 1 to 4 micromolar of the efficacious dose is pretty different than 9,400 micromolar or 15,000 micromolar for the lethal dose, and you'd say that, well, warfarin is kind of should be a pretty non-toxic substance, and there is toxicity, but not very much lethal toxicity for warfarin being used as a blood thinner. Okay, cool. Okay, another drug. Continuing the theme of kind of carbonyl aldol type of chemistry. So this is another very popular pharmaceutical. This is Fluoxetine. Of course, that's also called Prozac, which is one of these SSRI antidepressants. Okay, and okay, so molecules like Prozac are used for a variety of types of depression, major depressive disorder, panic disorder, other kind of related illnesses. It is a highly prescribed drug. I think in 2018 it was the 23rd most prescribed drug. It is a pretty easy molecule to synthesize, and it's also used generically at this point. Yeah, I think there's like 25 million prescriptions. Of it, I think. Okay, chemistry-wise, yeah, it's a couple steps of synthesis using these kind of simple reactions that we're discussing right now. I'll draw the molecule. We'll talk about the synthesis thereafter. So I'll draw the molecule down here. It is, and we have N-methyl, so you have NH there. And we have an oxygen and a benzene with a CF3 there. So that's actually pretty straightforward. Are there any chiral centers here? Is this a chiral molecule? The answer is yes. That's a chiral center, and that's actually going to be an interesting thing we'll come back to, because you could actually make the two different stereoisomers of Prozac, and they actually do have a little bit of a different activity, so there's a little bit of a rationale for maybe making a single enantiomer, but it turned out to not be a fruitful thing. I mean, it was explored, but in the end, people found that the racemic mixture is just as it was basically so easy to produce and efficacious, so that's the one that is used clinically. Okay, so clinically, the racemic molecule plus minus fluoxetine is the one that's used. Okay, so synthetically, they can build this from just attachment of the oxygen to a benzene. That's a weird place to connect. You know, that atom to that atom. Usually you'd think, oh, we'd make an ether, like a Williamson ether synthesis or something like that, but that's not. They did this slightly different commercially. And they actually make this bond also. So there's kind of like, we're going to take this left piece and sort of attach these two pieces, okay? Alright, so, and anything else to mention before we continue? The drug company that popularized this drug was Eli Lilly. They commercialized it, I think, in 1986. It was approved for medical use. Yeah. Okay, and yeah, I'll talk about SSRIs also in a bit. I have a little scheme that shows how they work roughly biochemically. Okay, so the chemistry of this starts with a very simple molecule. Acetophenone, which is acetophenone. And that's gonna be the sort of left part of the molecule. Dirt cheap chemical. This is 1 kilogram for $40, which is about as cheap as chemicals get for any kind of, well, I'm sure like ethanol might be a little cheaper than that, but for a a molecule with a benzene and a functional group, that's actually pretty cheap. Okay. All right. So first thing they do is, and I'll talk about the mechanism shortly, is they attach a dimethylamine group. Okay. Dimethylamino group. So, and a carbon, I guess, right? A carbon, nitrogen, and 2 methyls. That's a reaction called the Manic reaction. Manic, M-A-N-N-I-C-H. That's often a reaction we might skip in Organic 2, but it is in the book. It's kind of at the end. And it is a kind of combination of the aldol reaction, which we talked about a little bit, and the Michael. That's what a manic is. Okay. Alright, so we'll get back to that. But that's essentially take that, and then they add the nitrogen with the 2 methyls. Then the next thing they do is really simple. They reduce the ketone to an alcohol. And that is a simple Organic 2 reaction, or actually an Organic 1 reaction. What's the reagent to reduce a ketone to an alcohol really easily? It's NaBH4, sodium borohydride, NaBH4. Okay, so that's a very simple reaction. Essentially, H minus attacks the ketone, right? H dot dot minus, in quotes, attacks the ketone. And then you have a second step where it gets because it makes an O minus, the O minus grabs a proton from like methanol. 2 steps. H minus attacks, and then this gets a proton from methanol, and then you get the alcohol. Okay? Alright, and so that gets us, pretty close. Interestingly, they have 2 methyls here, and there's 1 in the product. So curiously, they're going to actually take one of those methyls off. That's kind of weird. Very weird to remove a part of a molecule like that. That'll be fun. We'll do that in a bit. Okay, so next thing is pretty simple also. They react with NaH. NaH, what does that do? NaH is a super base, and it's just going to rip off the proton from the alcohol. It's a base. It's a, it's another H minus. It's weird how this is kind of an H minus. It does one thing, and this is a H minus that does a different thing. Remembering that NaBH4 is kind of like a nucleophilic H minus that attacks like a ketone, whereas NaH, Na plus H minus, is a basic H minus, and it does base stuff like take the proton off the oxygen. Okay? Okay, so once they take off that proton from the oxygen, they are going to react it with this cool, pretty cool reaction, CF3 bromo. Okay. I'll mention the mechanism in a second, but it actually attaches the oxygen to that carbon with the Br. It's kind of a weird reaction. We'll do the mechanism in a few minutes after this. But what do you get? This is how they form that oxygen carbon bond I was talking about. Okay, so it's phenyl, oxygen, benzene, CF3. That's weird. How does it do that? I mean, that's actually a kind of an interesting mechanism question, right? How does it do that? How does it do that? Okay, this makes sense. This takes off the proton. So you have O minus, right? I can even do that. B dot dot is the base, it's the H minus. Takes the proton off, puts the electrons onto the oxygen. See that? Okay, that's that. Makes the O minus. And then that O minus attacks the carbon with the Br and kicks it off. Kind of like an SN2 reaction, but SN2 doesn't happen on benzene. That's like not the right substrate. So this is not an SN2 reaction. It's actually called an SNAR reaction. SNAR. And I always call this the Snar reaction. Snar. Yeah, I'll talk about the mechanism in a second, but it's weird that it's like the oxygen attacks the carbon, and then there's some funny stuff on the benzene, and then the Br goes away. It's called Snar. Okay, so we got Snar. Now we're very close to the product. All we got to do is take off that methyl group, and to do that, they do a pretty neat little reaction. Got to take off one methyl to make the product. So I'm going to kind of sneak down and react with Cyanogen Bromide, CNBR. This is a kind of fun name. Cyanogen Bromide. Cyanogen Bromide. And essentially what happens is nitrogen attacks the cyanogen, just like that. Kicks off the Br. Okay. And then that's gonna give us a method to take off one of the methyls. So that's what happens next. Pretty easy. It's a kind of clever way to remove a methyl group from a molecule. So we got our two methyls. We have our nitrile now, CN, and we got our oxygen. I'm just gonna say OAR for aromatic ring. That's the OAR is that thing. Okay. What's the charge on nitrogen now? It was neutral, now it's positive. Okay. Br minus, which you created, so we have Br minus, attacks one of the methyl groups, kicks electrons onto nitrogen, and that just removed a methyl group. So that's a neat trick to remove a methyl group, one of the methyl groups. Okay, so you make bromomethane, right? CH3Br in this method. Okay, what does that give us now? Almost the product. Phenyl, OAR, C triple bond N. Okay. And to finally finish this off, to make the commercial product, they use KOH, and that KOH will just sort of attack the nitrile and through a couple steps of mechanism I'm not going to talk about. Basically kick electrons up, down, and off, and this falls off nitrogen, so it cleaves the bond. And the end result is we got our product, Fluoxetine. Okay? Okay, so the things I want to talk about, is just as kind of a little fun mechanistic stuff, is the Manic reaction. How do we attach the dimethylamine? And also this Snar reaction. I just want to review that stuff. Okay. Alright, so first the Manic. The Manic was really the first step. Mechanism of the Manic. And I think that, I want to say it is in the latter, one of the latter Volhart short chapters, maybe 24, the amine chapter, question mark. It's one of those later ones. You can look in the index if you do want to research this a little bit more. Okay, so what is it? It's basically we're taking the ketone. We're reacting with formaldehyde also, which is just formaldehyde, yeah, and dimethylamine. Okay, kind of mix those things up, and it's essentially going to be an aldol followed by a Michael. I'll show those steps. And that gives us a ketone and 2 carbons, nitrogen, methyl. Okay, so just kind of all of that stuff attaches. Okay, so anyway, first step is the aldol part, and the aldol is really those two things reacting. So base takes the proton off the ketone, makes it enolate. It's called an enolate if it's an O-. So base takes proton, it makes it a little, not an enol, but an enolate. O-, blah blah, enolate. Okay? As opposed to an enol, which again was, this would be the enol, an alcohol, that's an enol. They're both nucleophilic, so that can go attack stuff, that can attack stuff. This is a little more nucleophilic because it's got the negative charge on it. Alright. So now the oxygen swings down, and then the double bond attacks, and electrons go up into oxygen. That is an aldol reaction. Okay, and now those two things are attached. We got phenyl, we got our ketone, we got alcohol. Yeah? Cool. Well, yeah, you technically have an O-, but we're going to assume that it got protonated from somewhere, so the proton got incorporated. Alright, so we have this. And then as the part of the aldol, if you remember the aldol, which you've probably forgotten this, there's always a second part of the aldol, which is minus water. So essentially, this proton and that OH will go away to make water, and it makes a double bond. So it makes a double bond. Cool. All right. That's an aldol product, the typical aldol product. Aldol product. And the name of the aldol product, we say it's like a ketone, right? We start with a ketone, we end with a ketone. But this is a ketone with a double bond between the alpha and beta carbons. That's like the alpha carbon and the beta carbon. So the way we usually teach this, we give it a name. We say it's a alpha, comma, beta. Alpha refers to that, the beta refers to that. Unsaturated ketone. Unsaturated ketone. Alpha, beta, unsaturated ketone refers to, what does unsaturation mean? It means the double bond, right? Alpha, beta, unsaturated ketone. Pretty much all aldol products are alpha, beta, unsaturated. Ketones are aldehydes. Okay. So what do we have to do to finish this off? Maybe incorporate that amine there. And this is where the Michael happens. So it's really just H and methyl, dimethylamine. And lone pair attacks, And remember that the double bond is an electrophile. It likes to be attacked, and that's all we're doing. We're having a nucleophile attack the carbon there, kick the electrons up onto the oxygen, and that's called a Michael-reaction. That's all a Michael-reaction is. So a Michael-reaction always requires something like an alpha-beta unsaturated ketone or ester, or alpha-beta unsaturated something. And then it's usually going to be like a nitrogen or some kind of nucleophile attacks, and you do the Michael-reaction. Okay? So that's almost the product. Now we got a phenyl, O minus. We got a double bond, carbon, carbon. What's it? 1, 2, 3, 1, 2, 3, 1, 2, 3 carbons. Nitrogen, nitrogen. Methyl, methyl. Yeah. Okay, and now to finish it off, it's just like water or something gives a proton. I'll just draw it down here. H2O. And we go back from the enolate to the ketone product. So this swings down, this goes there, and we're done. So that's the Manic reaction. All it did was easily gave us a way to take a ketone and then add an extra carbon and a nitrogen with some stuff on it and then make this. And that is the best way to do that. So the Manic reaction is very useful for a lot of drug synthesis because drugs often contain a nitrogen like that, maybe a couple atoms away from a ketone. Okay, that's the Manic. Let's do the Snar now. And yeah, just so to review what we mean by Snar. Snar is going to be the reaction where we basically take this alcohol, like as a nucleophile, react it with the bromobenzene. It's kind of an electrophile, and then make the ether linkage right there. And it's not SN2. Not you might think, oh, it's just, you know, O minus attacks the carbon, kicks off the Br. It's not exactly that. It's a slightly different, kind of cooler mechanism. That's what we call Snar. Okay. Okay, so let's talk about the Snar thing. I'm gonna give a real quick example of a Snar. This is a typical example from chem842. I think it's in VS22, chapter 22. Just to remind us what it is, Snar. Snar is SNAR. And those letters stand for substitution, nucleophilic. That makes sense, right? Substitution, nucleophilic, aromatic. Okay, so the kind of classic example of a Snar reaction that we always teach in, you know, like organic or something, is got like a NH2, which is a nucleophile, whatever. And I have a molecule that looks like this. Well, you need this thing like a nitro, which is a electron withdrawing group. It's like sucking electrons away from the benzene, right? And then we're going to have like a leaving group, bromine, like this, okay? Okay. So those two things are going to react, and the nitrogen is going to get connected. This is going to be kind of like our little molecule with the Prozac synthesis, okay? Alright, so the product is simply going to be nitrogen, and that. Okay, cool. So how does it do this? How do these two things react and make this product? I rotated a little bit there. Okay, so you might again think nitrogen just attacks and kicks off the Br, but it's not exactly what happens. What actually happens, it does attack, but the nitro has to play a part, because without the nitro it doesn't work. Prozac has that CF3, and that's going to have the effect of the nitro. Okay. So it kind of attacks, and then pushes all the way onto the nitrogen of the nitro. Okay. All right. So those two things kind of connect, and HH plus charge. Okay. Then we still have our bromine on there. Double bond, nitrogen, O minus, O minus. Kind of weird looking little intermediate like that. Alright. And then, what do you think happens next? That might get rid of the Br and return the nitro back to its normal nitro structure. Any guesses? Okay, well, one thing is a base takes this proton. That's not that exciting. Okay, that probably happens. But yeah, pick an O minus. We'll use the top one, I guess. Swings back. Then this goes there. This goes there. This goes away, and you get the product. So that's how that's a Snar reaction, right? It's a two-step process. Nucleophile attacks, electrons go all the way to the nitro or whatever, and then it swings all the way back and kicks off. And this complex actually has a name. It's called the Meisenheimer complex. Kind of a weird name, but it's I think a German scientist that discovered this a million years ago. Okay, all right. So now back to the Prozac example. It's a similar idea. I'm just going to draw isopropyl alcohol as our little secondary alcohol, and the way they do this is oxygen, and then they connect to CF3 like that, essentially, right? And this one NaH, sodium hydride, is a strong base. 2 is the bromo, benzene, trifluoromethyl, CF3. Alright, so how does that work? How does that work mechanistically? NaH, again, is a super base, is essentially Na plus H minus. Right? And what's it going to do as a base? Take off the proton. Proton gets taken off, you're left with a O minus. Oh, you know, the one thing I should do, I gotta be real careful here. Don't draw the circle on the benzene here. Let's get rid of all the circles. The circles here will be confusing because we actually need to show each of the bonds for this to work. Okay. Alright, so now we have this thing with the O minus, dot, 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 minus, alright? And what do you think is going to happen? Well, just like before with the nitro, this thing will just attack. But the difference is we don't have a nitro, right? We have a CF3. I'm going to redraw this one more time, I'm sorry. Nice and clear. Okay. Bromine. There we go. But the CF3 can kind of serve the role as the nitro. That's the point here. If you don't have the CF3, this won't work. So this reaction kind of depends on that CF3, and also, I guess, that would depend on, you know, the CF3 being important in the drug, because if the drug didn't have a CF3, or, you know, we probably couldn't use this synthetic approach. Okay? But anyway, so the oxygen attacks, and rather than it go all the way into the nitro, it kind of just goes like right there. And that's going to be the Meisenheimer complex. Actually, so that the now it looks like double bond, like that. Yeah. Let's erase this stuff. Okay, so the thing is, the reason this works is because this negative charge is still stabilized by the CF3. The CF3 is an electron withdrawing group, so it's kind of pulling electrons towards it, and right. So it can stabilize this in a slightly different way than the way the nitro did it. The nitro actually pulls it all onto the nitro, but this thing is a stabilizing group, and that's important. Stabilizing group. If you don't have any kind of stabilizing group, it doesn't work, right? Okay, so anyway, we can draw a bunch of resonance structures if we wanted to. I'm not going to do that. If I wanted to resonate, I could push the negative charge there, put negative there. The negative would be, drawn to the fluorine. Bunch of resonance, nice stable thing. But in the very end, it just swings back and kicks off. And now you make the final product. Cool. So that is how Snar is used to build the key ether linkage in Prozac, which is really that bond, right? That's the bond that's created there. Okay, cool. All right, so that's pretty much it for the synthesis of Prozac. Okay, so we're basically done. I just want to quickly show my little cartoon slide for how SSRI drugs are kind of thought to work on the serotonin receptor system. A couple drugs have this kind of activity: fluoxetine or Prozac, sertraline, Zoloft, or citalopram, which is Celexa. And anyway, so you may have seen this in like a biology class or something. The idea is that we're trying to kind of increase the amount of serotonin in the receptor, and that apparently has the sort of an antidepressant effect. All right. So how does this all work? So if you look at a neuron, basically serotonin is a neurotransmitter that's packaged into these little vesicles, and then in the presynaptic neuron, the vesicles are released, and then that kind of creates serotonin, or it releases serotonin molecules in this little cleft, and then they bind to the serotonin receptor. Okay, and that kind of creates, it's a neurological signal. The idea is that if you can increase the amount of serotonin in the receptor, that it has an antidepressant effect, and there seems to be evidence for that. Okay, and so after serotonin is released, and then basically, after it binds to the receptor, the molecules are released, and they're taken up into this transport protein, which recycles them. Okay, and that is called reuptake, right? Serotonin reuptake. All right, and then the molecule fluoxetine, as an example, will sort of block the reuptake process. All right, so the end result is after you take a drug like this, like Prozac, if you're blocking the reuptake, that basically has more serotonin floating around in the cleft and more likely to bind to the postsynaptic neuron, and that creates more activation of the serotonin system, and that kind of improves treats depression, we'll say, or treats some of the symptoms that people suffer in depression. And that's at least the theory, and I think there's a lot of evidence that this works. But that's basically what they do. That's what the SSRI drugs do. Okay, all right. I think we're done. And I just wanted to give a little bit of information on this, and I mean, there's a lot more complexity to SSRIs and what they do. But that's it in a nutshell, because they're essentially an indirect agonist of the serotonin receptor by inhibiting serotonin reuptake. They're inhibiting the serotonin reuptake transport protein. Okay, cool.